Thank you for coming to the dependent type sessions, our final session for today. Our first speaker is Nils Danielsson. He's going to be speaking about how to use size types in order to do, I think, bisimilarity proofs, something like that. So, Nils Anders.
Thank you. So what I said this morning was that if you use size types to define bisimilarity, then you get sort of a class of up-to techniques that falls out naturally. And now I'm going to try to explain what I meant this morning. So what's an up-to technique? So up-to techniques are often used to define bisimulations. And if we take the bog standard example of CCS, then we have something like this. So R here is the bisimulation if whenever P and Q are related by R and P can make a mu transition to P prime, then Q can make a mu transition to some process Q prime such that P prime and Q prime are related. And the same on the other side. So if P and Q are related by some bisimulation, then we say that they're bisimilar. And this gives us a notion of equivalence for processes. Now, proving this directly can be a bit awkward. So people have come up with ways to make it easier. So here's one example. R is the bisimulation up to bisimilarity. Well, down here, it's a bit easier now, because now we can prove that P is bisimilar to some process that's related by R to some process that's bisimilar to Q prime. And this works in the sense that if P and Q are related by some bisimulation up to bisimilarity, then they are bisimilar. And more generally, there are lots of functions, f, that we can put here that make this work in a sense that this suffices to prove that P and Q are bisimilar. And these are called up-to techniques. Now, I'm interested in dependently typed programming, and in a dependently typed language like Agda, for instance, it's quite natural to define bisimilarity as an indexed co-inductive data type, so a data type with infinite values, infinite proofs, in this case, proofs of bisimilarity. And it can be a bit awkward to work with these co-inductive data types, but if you use size types, for instance, then it can be easier. And if you use size types, then it turns out that the class of up-to techniques falls out naturally, and that's what I'm going to try to explain. So I'm going to start by trying to explain what size types are and how they help you, and then talk about an example that is intended to show you what I mean by this. So let's start by co-inductive data types, and I'm going to start with an example that does not have size types, so that I can show you how size types help you. So this is a type of potentially infinite list that could be infinite. And well, I'm using Agda notation here because Agda is, as far as I know, the only fairly mature language with support for size types. So here's one way that you can define these co-lists, potentially infinite lists in Agda. So we have the nil constructor and we have the const constructor, so kind of like with regular lists, but for the tail here, I'm using co-list prime instead, and you can think of co-list prime as being the type of suspended co-lists. So here we have this record type here, and if you force a suspended co-list, then you get a co-list. And here's one example of how you can define a function for a co-list, the map function that maps a function over all the elements in the list. So for nil, we get nil. For const, we get const, where we map the function over the element. And then we continue here with a suspended co-list. And I'm using an auxiliary function here to define that. And this function is defined using a co-pattern. So this says that if we force map prime of f and x's, then we get map f and force x's. Now, writing this with an auxiliary definition is a bit verbose. So I'm going to write this using an inline co-pattern instead, but it means the same thing. Now, if you're working in a type theory like Agda or Coq or something like that, and where you're working with co-inductive data types, then typically you want your definitions to be productive, meaning that you can get the next element, the next constructor, in a finite number of steps to avoid inconsistencies and so on. And this definition is productive. You can see that you always get the next constructor quickly when you force and continue working and so on. But it's not enough that it's productive. You should be able to tell Agda. Agda should understand that it's productive. And in this case, Agda can see that it's productive by using something called guarded co-recursion. So you can see that the co-recursive call to map here is below this co-pattern and this constructor, and there's nothing else in between. And because of this, because the program falls into this fragment, Agda says, yes, that's okay. But in many cases, it's not okay. I mean, Agda fails to see that many productive definitions are okay. And here's one example. So this is intended to be the list of all the natural numbers, 0, 1, 2, and so on. And it's defined to be, well, we start with 0, and then we take the list of natural numbers and add 1 to every element. So when we add 1 to 0, 1, 2, we get 1, 2, 3, and so on. So that's 0 followed by 1, 2, 3, and so on. So this definition is productive if you see it as a lazy functional program, but it's not guarded because we have this function in between the co-recursive call and the top level here. So this definition is rejected, and this makes it kind of awkward to work with co-inductive definitions. And people have come up with various ways to make it easier, and one such method is size types. So let's see now what happens if we take this definition of co-list and turn it into a sized co-inductive definition. So now we have this size parameter here, and we just pass it down to the suspended co-list, but down here we have something more interesting happening. When we force the suspended co-list now, we should give a size that's smaller than the size that it had before. And then we get this co-list of this smaller size here. So you can think of co-list prime IA as being partially defined co-lists of depth at least I, meaning that it's safe to force these things sort of I times, as long as we get new cons constructors all the time. And there's also a special size infinity standing for fully defined co-lists. So co-list prime infinity would correspond to the thing we had before. And now let's look at the map function. So here the map function, we can keep exactly the same body as before, just update the type signature. And this says that for any size I and any function from A to B, if we have a co-list of size I containing A's, we get a co-list of size I containing B's. So you can see that now this is a size-preserving definition, meaning that, well, the size here is preserved in the output. And that's going to be a central topic here today. If we look at the NATS definition, now we can keep exactly the same code as before, just change the type signature. Now this definition is accepted. And why is it accepted? Well, let's expand the definition to see what the sizes are. So we should define a co-list of size I here. So we do 0, 0 cons, and then here we should define a suspended co-list of size I, and then when this is forced, we get the size j, which is smaller than I. And here now we should define a co-list of size j, and because map is size preserving, that means that here we should define a co-list of size j, and that's what we're doing with this co-recursive call. So the types make sense, and furthermore, because this co-recursive call is at a smaller size, Agda accepts this definition. Well, this plus some technical condition that I don't want to go into. So size types make it a bit easier to write code because you can write code that looks more like what you would want to write. Okay, let's see how this can help us with bisimilarity. In order to define an example later, I'm going to introduce a very small process calculus. It's going to be defined using a label transition system, and to make things simple, I have one label, dot. And I have just a few process constructors. There's a nil constructor for a process that doesn't do anything. We have parallel composition, and we have prefixing with a dot. So prefixing, well, dot p is basically emit the message, dot, and continue as p. But to make this a bit more interesting, I'm defining this using mixed induction and co-induction, so you can have infinite processes. So you can see here that this thing is a suspended process argument, but only for dot, not for parallel composition. So if you want to have infinite processes, you have to use dot. And now we can also define this transition relation for this system. And it's defined using induction, so it's just like a regular inference system. So there's no rule for nil because nil doesn't do anything. We have the rule saying that dot p can make a dot transition to force p. And then we have two rules for parallel composition. So if p can make a mu transition to p prime, then p in parallel with q can make a mu transition to p prime in parallel with q, and similarly for the right-hand side. Of course, this is a very, very basic process calculus. There's not even any communication here. But what I'm saying is going to, it works also for more interesting systems. So if you look at my paper, you can see a proper variant of CCS with communication and replication and so on. So how can we define bisimilarity now? So recall this definition of what it means to be a bisimulation. Bisimilarity is often defined as the largest bisimulation. We can turn this directly into a co-inductive definition in this way. So here I'm defining bisimilarity between P and Q of size I. And we have two fields here. This one says that if P can make a mu transition to P prime, then there is some Q prime such that Q can make a mu transition to Q prime. And P prime and Q prime are bisimilar using this suspended variant of bisimilarity of size I. And this is defined in the same way as before with the smaller size and so on. And the right to left part is just, well, the right to left part. Now, if you take this thing and instantiate the size here to be infinity, then it's easy to prove that this is logically equivalent to the standard definition using bisimulations. So what can we do with these definitions now? Well, we can prove that bisimilarity is transitive, for instance. That's the property that should hold. So if P and Q are bisimilar and Q and R are bisimilar, then P and R are bisimilar. And moreover, this sort of obvious proof that you write down turns out to be size preserving. So if this bisimilarity proof has size I and this one has size I, then we get a proof which has size I. We can also prove a bunch of preservation lemmas. So we can prove that the parallel composition preserves bisimilarity. So if P and P prime are bisimilar and Q and Q prime are bisimilar, then P in parallel with Q and P prime in parallel with Q prime are also bisimilar. And again, this is a size-preserving proof. And similarly, we can prove that prefixing preserves bisimilarity. So if force P and force Q are bisimilar using this suspended variant of bisimilarity, then dot P and dot Q are bisimilar. And again, it's size-preserving. And then the final lemma I'm going to use is the fact that nil is a left identity of parallel composition. And all of these proofs are very simple to prove, but I'm not going to show you the details. So now we get to the main example here. I have two simple processes. P here is nil in parallel with dot P prime in parallel with dot P prime, where if you force P prime, you get P. And Q is dot Q prime in parallel with dot Q prime. And now I want to prove that these two processes are bisimilar. And here you have a proof. So the proof says that, well, for any size I, P and Q are bisimilar of size I. And of course, then if we instantiate I to infinity, we get that they're actually bisimilar. So how can we prove this? Well, we can use transitivity first to remove the nil from P. And then we can use the preservation lemmas, one for parallel composition and two for the prefixing. And then we can continue co-recursively with the proof here. And because this and this and that, because these are all size preserving, we know that the smaller size we get here is actually smaller than the size we start out with here. So this is a proper definition. It's accepted by AGDA, and it's productive. So now I want to make some observations about this proof here. So if we look at the use of transitivity, which is here, we can compare that to the up to bisimilarity technique. So with up to bisimilarity, we can combine bisimilarity proofs with the thing we are defining here. And that's sort of what we're doing here. We're combining this bisimilarity proof with the thing we are in the process of defining here. So the transitivity proof, because it's size preserving, it kind of gives us up to bisimilarity. And similarly, we can compare the preservation lemmas to up to context. So up to context says that, well, we can replace R here with the context closure of R. And that's sort of what we're doing here with these things. We're taking some the context with parallel composition and the two dots here. So this kind of gives us the up to context technique. And in both of these cases, these proofs are size preserving, so we can combine them in any way we want, as long as the types make sense. So these sort of up to techniques that we get here are compositional in that sense. We can combine them. And furthermore, when you define bisimilarity, it's quite natural to want to prove transitivity. And if you just prove that in the obvious way, then you don't actually need to do anything to get to make this into a size-preserving proof, except for writing this down in the type signature. And similarly for the preservation lemmas. So you kind of get these up-to techniques for free, kind of. And that's what I mean when I say that the up-to techniques fall out naturally. Okay, so this is an example of something that works. Now let's consider something that does not work, where something is not size-preserving. So we can consider weak bisimilarity. Well, not for this toy calculus that I presented, but if you take full CCS, we can consider weak bisimilarity, where we basically ignore silent transitions. So this is another equivalence that's often used. And now we can repeat this exercise. We can define weak bisimilarity in a similar way. And we can try to prove various lemmas. And if we try to prove these preservation lemmas, it turns out that we can prove lots of size-preserving preservation lemmas for CCS. But transitivity is a bit different. So weak bisimilarity is still transitive, but it's actually provably impossible to prove that to prove transitivity in a size-preserving way. So we can prove transitivity in this way. So if P and Q are bisimilar at size infinity, and similarly for Q and R, then we get a fully defined bisimilarity proof between P and R. But it's impossible to replace these with a size I, an arbitrary size I. Fundamental problem of weak bisimilarity. So you may have heard of the it's a paper from 1992 where Sangiorgi and Milner pointed out this limitation of weak bisimilarity that's sort of been haunting this field since. And this problem, well, the problem is that weak bisimilarities up to weak bisimilarity are not in general contained in weak bisimilarity. And this problem implies that you cannot do this in a size-preserving way. So I focused on bisimilarity so far, but you can define up-to techniques in a much more general setting. And if you work in this setting, then every predicate transformer that's size-preserving in a certain sense turns out to be an up-to technique. And furthermore, this class of up-to techniques that you get in this way is close under composition, so that it's easy to combine them. And that property does not hold for the full class of all up-to techniques. That class is not close under composition. Oh, by the way, I don't want to make the claim that every size-preserving technique in this class falls out naturally, sort of for free. I don't want to make that claim. But it's interesting to compare this class of size-preserving up-to techniques to a class that Damien Pous introduced a couple of years ago in a paper. So his class is based on functions below what he calls the companion. Now, this class has received quite a lot of attention in the last couple of years, and indicating that people find it useful. And these classes turn out to be closely related. I haven't been able to nail down exactly how they're related, but I could prove that they're equivalent by adding a couple of axioms to AGDA, but I'm not quite sure if these axioms are actually consistent with AGDA, so take that with a grain of salt. But they seem to be very closely related, at least. And it's an open question exactly how they're related. But I find it interesting that even though I came at this from a somewhat different angle, we ended up with classes that are rather similar. But I don't plan to show you any details of exactly how all these definitions work. So I leave that for the paper, or you can ask me. So, but my main message here is that when you're using a type theory with size types, as like AGDA, for instance, to define bisimilarity using co-induction in the way that I presented, then it turns out that a class of up-to techniques kind of falls out naturally. And I hope I've made that a bit more clear now with this presentation. Thank you.
So what does the size less than mean when you have a size of infinity?
Yeah. So the way it's done in AGDA at the moment is that infinity is less than infinity. But this has led to some sort of weird corner cases, so that should probably be changed. So, by the way, I should probably say that no one has worked out the sort of complete consistency of size types the way it's done in AGD at the moment. So that's still an open problem that people are working on.
So one problem that's quite related to the problems of bisimulation up to, especially weak bisimulation up to weak bisimulation, is for applicative bisimilarity. And their applicative bisimilarity for higher order transition systems. And there the solution is Pous technique. So I was wondering whether, in the same way that bisimulation up to is falling out of size types, whether Pous technique would fall out, which would be quite nice.
I haven't thought of that. I mean, I would doubt it, but I mean, yeah, I don't know. I mean, Pous technique is sort of very technical. It would be nice if you could, yeah, I don't know.
All right, thank you.
So the standard way of getting around the weak bisimilarity problem is to have weak bisimilarity composed with your relation composed with strong bisimilarity. And then you do get an up-to technique. Would this work in your setting? Or it was a bit unclear to me what this, you had this function f and a relation, and then you had your up-to technique, but exactly what you require of this f was not entirely clear to me.
So this is the sort of full definition of what
Right.
it means for a sort of a predicate transformer to be size preserving.
Mm-hmm.
So if you're working with some functor and you have this predicate transformer, then this predicate transformer is size preserving with respect to this functor if for any predicate, if this predicate is below the ith stage of the greatest fixed point of the functor, then it should be then FR should be below the ith stage. That's the sort of condition.
So did you try the composing with strong bisimilarity in the end for weak bisimilarity?
So
you have weak bisimilarity composed with a relation, composed with strong bisimilarity. Then you get an up-to technique that actually does work. So what this means is that the first action must actually match. But
All
then
right.
you can go off and be weak bisimilar. All right, so.
I haven't tried this. We can talk about that later.
Is there time, or I can put?
Yes.
Can you use the strengths of size types to go beyond up to techniques? Do you have interesting examples where you actually don't preserve the size, but then recover, and through the arithmetic of size types, you obtain a valid composition?
Are you asking about the sort of arithmetic of sizes?
Yeah, so essentially going beyond, because there is the potential to go beyond up to techniques, right, using size types. I mean, does it apply here? Obviously, in function definitions, you can get interesting results, but here, for proofs about process algebra and such, do you have examples where you could do that?
Well, I mean, in the language where size types is used for ensuring termination and productivity, then of course, everything you can do with size types, because that's the way you do it. So I'm not quite sure exactly what you mean.
No, so I'm saying that you could probably go beyond up to techniques.
Yeah.
Concerning proofs of bisimilarity in process algebra. But for instance, weak bisimilarity is probably it doesn't qualify here because it's unbounded in a way. But
I mean, this is an application of size types. It's not everything you can do with size types.
Right. Yeah. Okay. Thanks.
All right, let's thank our speaker.